Under this module, today we are going to learn that how the distortions from the regular octahedral geometry takes place, and secondly, why the distortions in octahedral complexes take place. Basically, there are various phenomena. Some of them are listed below, like Jahn-Teller distortion. Also, we are going to discuss that why the color and magnetism in the coordination complexes is there. After learning this module, you shall be able to learn the factors which influence the extent of distortion in the complexes. Also, we will identify the reasons for color formation in the coordination complexes. Again, we are going to evaluate the magnetic moment of various transition metal ions. So, introduction to distortions from the regular geometry. Some of the complexes having 6 surrounding ligands possess structures which are not octahedrally symmetric and are considered to be tetragonally distorted. These include large number of copper 2+ complexes. Other species such as D8 compounds possess only 4 ligands forming a square planar geometry. These types of complexes have a ligand field effect which is different to both the octahedral and tetrahedral cases, though it is useful to use the octahedral case as the basis for discussion of the tetragonal as well as the square planar geometry. A tetragonal compound can be generated from an octahedral compound if we stretch the metal ligand bond along one of the axes which is conveniently chosen as the z-axis. Now we'll discuss how the distortions in octahedral complexes takes place. Under this, first of all, we are going to discuss Jahn-Teller distortion. According to this theorem, if the ground electronic state of a nonlinear complex is orbitally degenerate, the complex is unstable, and in order to sustain the stability, it must distort itself so as to remove the degeneracy and hence achieve the lower energy. In other words, it can also be said that the unequal occupation of the orbitals with identical energy is unstabilized, and hence it has to distort in order to eliminate degeneracy. The Jahn-Teller effect only predicts that which of the structures is going to undergo distortion, but the extent of distortion and the geometry of the distorted complex cannot be told by this theorem alone. In the case of octahedral complexes, we have 2 sets of orbitals, e.g. which directly point at the approaching set of ligands, and T2G which lie in between the axes and hence are not placed directly in the path of the ligands. Now, since EG orbitals are having greater interaction with the ligands in the path of the ligands, hence the Jahn-Teller effect is more pronounced, and in these cases, which include high spin D4, low spin D7 and D9 configurations. The distortions in the case of octahedral complexes are also called tetragonal distortions. It can be seen in the figure that we are having a high spin D4 case which is possessed by chromium 2+ as well as manganese 3+ ions, D7 low spin case which is possessed by cobalt 2+ and nickel 3+ ions. Also, we have D8 low spin cases which is there in cobalt 1+, nickel 2+, palladium 2+, rhodium 1+, platinum 2+, as well as gold 3+ complexes. The D9 case, which basically undergoes the Jahn-Teller distortion most efficiently, is comprised of copper 2+ complexes as well as silver 2+ complexes. Here we have shown that how the filling of electrons in the d orbitals take place when it leads to the distortion. Considering a D4 or a D9 situation, octahedral geometry is degenerate since the last electron can either occupy dx square y square orbital or dz square orbital, which is comprised in the Eg level. Thus, a Jahn-Teller distortion in which Eg level splits into a dz square orbital and dx square y square orbital, and thus degeneracy of the Eg level is lifted. There occurs a net reduction in energy, or we can say there is increase in the value of crystal field stabilization energy when the degeneracy is lost due to distortion. The tetragonal distortion may occur by either elongation of the z-axis or by compression of the x and y axis. The Jahn-Teller effect cannot say that which one of the distortion is going to take place, but it only tells that yes, distortion will occur. There we have shown a diagram that how the Jahn-Teller effect leads to the elongation of the z-axis on the left hand side and how the compression of the x and y axis takes place on the right hand side. Now we will consider a D9 case where the last electron has to occupy the Eg level. In that level, it is an option that either it can occupy a dz square orbital or it can occupy a dx square y square orbital, since both of them are degenerate in energy. Now, if we will consider that electron is going in dz square orbital, the orbital interaction of the electron with the approaching ligands will finally lead to lowering in energy of the dz square orbital, and thus this will lead to tetragonal elongation where the z-axis is elongated. This incoming ligand along the z-axis to a greater extent as compared to x and y axis. Consequently, the z-axis is elongated as relative to the x and y axis. In the otherwise situation, if we'll consider the last electron is going to occupy x square y square orbital, the electronic interaction will finally lead to lowering of energy of dx square y square orbital, and thus we can say that z-axis appears to be compressed as compared to x and y axis, and thus it is called z-axis compression or tetragonal compression. Table 1 is given, which shows the number of electrons and high spin Jahn-Teller theorem and low spin Jahn-Teller theorem followed by these configurations. The T2G orbitals are also affected by the distortion, but since they lie in between the axes and their extent of distortion is less, hence we can say for the tetragonal elongation, the orbitals from T2G set having contribution from the Z component will undergo lowering in energy in the compression case as compared to the greater contribution from X and Y axis. If the tetragonal distortion is fluxional, that is, the extended axis in the tetragonal distortion changes with time, that is, the time scale of existence of one fluxional form is changed or transformed to the other before the time scale is measured. Hence, we can say that we can have an average structure of the compound when elongation along each of the axes is equally favorable, as is suggested in some of the cases like copper complexes, where all the ligands are the same. Observed average geometry is the octahedral geometry. This fluxional variation of the distortion from one orientation to the other is shown or known as the dynamic Jahn-Teller effect. Now we'll discuss the formation of the square planar complexes. We can say the formation of square planar complexes is an extreme case of tetragonal distortion, where the z-axis is so much elongated that ligands along it are seen as not being present in the vicinity of the metal ion. We can say that the z-axis then disappears and only 4 of the ligands are left, giving rise to the square planar complex. The dz square orbital will be lowest in energy as it has negligible interaction with the ligand field. This gives rise to a situation where instead of 6 but only 4 ligands are present about the metal center, leading to a square planar complex. This kind of distortion occurs when the new geometry has a greater ligand field stabilization energy as compared to the original octahedral complex. In other words, we can say that formation of square planar complexes basically occurs in order to achieve the ligand field stabilization energy more as compared to the original octahedral complex. For example, if the original complex is an octahedral D9 case where the configuration is T2J6 Eg3, the tetragonal distortion will definitely take place, since it means that the 2 electrons in the Eg orbitals move to the lower energy and one moves to the higher energy. So the overall effect that we have a net reduction in energy and the distorted environment is more stable. This can be seen in figure 3. In the D8 situation, the extreme of distortion gives full occupation of the lowest lying dz square, dxz, dyz and dxy orbitals and an empty dx square y square orbital, also resulting in an increase in the CFSE value. When the square planar geometry is adopted, the d orbitals of the metal now have 4 different energies, and so 3 splitting parameters may be defined. If we consider only the total splitting parameter, that is delta SP, where SP stands for the square planar, which is in the fact the sum of 3 intermediate splitting parameters, we'll find that it is actually larger as compared to the octahedral splitting parameter, that is delta SP is equal to 1.3 times of delta naught, where naught suggests that we are talking about an octahedral field. The square planar coordination can be imagined to result when the 2 ligands on the z-axis of an octahedral are completely removed. This gives leaving only the ligands in the xy plane. As the z ligands move away, the ligands in the square plane move a little closer to the metal ion. The orbital splitting diagram for a square planar coordination complex can thus be derived from an octahedral diagram. As the ligands move away along the z-axis, the z orbitals with a z component will definitely fall in energy. The dz square orbital falls the most as its electrons are concentrated in the lobes along the z-axis. The dxz and dyz orbitals also drop, but the energy is not as much dropped since they are pointing not directly toward the ligands, or we can say their orbital ligand interaction is quite less. Conversely, the dx square y square and dxy orbitals are increased in energy. The formation of a square planar complex has been shown in figure 4, where we can say that how an octahedral geometry finally gives rise to a square planar complex. Now we'll be talking about the color and magnetic properties of the coordination complex. In this, first of all, we are going to discuss that why color in coordination complexes is first of all there. The color in the coordination complex is a consequence of splitting of the d orbitals. Partly filled d orbitals absorb radiations in the visible region of the spectrum so that to make the d electrons transit from a lower energy level to the higher level. Color of the complex is light reflected by the complex, which is actually complementary to the light absorbed by the complex. Color of the complex depends upon the nature of the central metal ion as well as the ligands surrounding it. Different ligands generate different ligand fields, and different strength, and hence diverse colors can be seen for the coordination compounds. For a given metal ion, weak field ligands generate a complex with smaller delta value which will absorb light of longer wavelength, that is lambda, and thus lower frequency, that is mu. On the contrary, when we have a strong field ligand, they will create definitely a greater amount of splitting which will absorb a light of shorter lambda and hence the higher frequency. It is though rarely the case that energy of the photon absorbed corresponds exactly to the size of the gap. There are other things such as electron-electron repulsion and Jahn-Teller effects that also affect the energy difference between the ground and the excited states. The color wheel, which has been demonstrated in the figure 5, can be seen that which color a compound will appear if it absorbs a color from the visible spectrum. Now we are going to discuss about the DD transitions taking place in the coordination complexes. When we talk about DD transition, we say an electron in the lower d orbital of the metal ion is excited by absorbing a photon and hence it departs to the higher d orbital. When we are having centrosymmetric complexes, the DD transitions are forbidden as given by the Laporte rule, which says that only transitions which are possible are which having delta L value of plus minus 1, and thus because of that the DD transitions are forbidden. However, due to some relaxation in the Laporte rule, we can say that these transitions actually occur. However, forbidden transitions are allowed if the center of symmetry is disrupted. Transitions that occur as a result of an asymmetric vibration of the molecule are called vibrionic transitions, since they are allowed because of the vibrionic coupling. For example, an octahedral complex of manganese 2 ion which has a D5 configuration in which all the 5 electrons have a parallel spin. The color of such a complex is much weaker as compared to the complex with high spin allowed transition. In fact, many compounds of manganese 2 like manganese 2 chloride appear almost colorless. Tetrahedral complexes have somewhat more intense color, which is possible because of the DP mixing which occurs in the absence of center of symmetry in the tetrahedral complexes. Therefore, the transitions are not exactly the pure DD transitions but a DP mixed kind of transition which is allowed due to the mixing of D and P orbitals. Now we will be discussing some of the magnetic properties of the coordination compounds. Under this heading, first of all, we'll see that how the magnetism in the coordination complexes appear. The magnetic behavior of the coordination complexes can be very easily explained on the basis of crystal field theory. In general, the ligands having high splitting ability leads to the formation of low spin complexes, since the gap between the T2G and the EG level is quite high. On the other hand, a low field ligand will lead to the formation of high spin complex where the gap between T2G and EG level is quite low. Now we'll consider the formation of a complex, cobalt complex, where ammonia is present as 6 coordinated ligands, and to that we'll discuss again a cobalt complex with 6 fluoride ligands. Now discussing both the cases, it can be seen that the central metal here, that is cobalt, is +3 oxidized in both the cases and possess an octahedral geometry. But the complex where we are having ammonia as a ligand is a low spin diamagnetic complex, whereas when we talk about fluoride as the ligand, it can be seen that it forms a high spin complex. A low spin complex means it is diamagnetic. It means that all the electrons are paired up. whereas in the case we are talking about high spin complex, it means it is paramagnetic in nature, which possess the unpaired electrons. This can be very smoothly explained on the basis of different ligand coordination that is taking place with the same central metal ion, that is cobalt 2+. When we talk about ammonia, it's a strong field ligand and hence leads to larger value of splitting of the crystal field, which creates a low spin complex, whereas when we talk about F negative, which is a very weak field ligand, in this case the rise in the low value of splitting and thus occurs the formation of high spin paramagnetic complex. This difference can be explained figuratively. Again, the ligands lying at the extreme end of the spectrochemical series present high field strong ligands and form low spin complexes. The examples include ethylene diamine, Cn negative, CO negative, etc. This is the diagrammatic representation of the paramagnetic versus the diamagnetic configurations. The magnetic moment value can be represented as mu and measured from a spin-only formula, which assumes that magnetic moment is basically arising from only the unpaired electronic spin. The formula is mu s, where S stands for the spin-only formula in the case of transition metal complexes is equal to n plus n by 2 whole raised to the power half. It means n represents the number of unpaired electrons. Now, why we can say that in the case of transition metal complexes, the spin-only formula works? This is because when we talk about transition metal complexes, we are talking about d electrons taking part in any complexation. The d complexes in general, the ligands having high splitting ability leads to the formation of low spin complexes, since the gap between the T2G and the EG level is quite high. On the other hand, a low field ligand will lead to the formation of high spin complex where the gap between T2G and EG level is quite low. Now we'll consider the formation of a complex, cobalt complex, where ammonia is present as 6 coordinated ligands, and to that we'll discuss again a cobalt complex with 6 fluoride ligands. Now, discussing both the cases, it can be seen that the central metal here, that is cobalt, is +3 oxidized in both the cases and possess an octahedral geometry. But the complex where we are having ammonia as a ligand is a low spin diamagnetic complex, whereas when we talk about fluoride as the ligand, it can be seen that it forms a high spin complex. A low spin complex means it is diamagnetic. It means that all the electrons are paired up, whereas in the case we are talking about high spin complex, it means it is paramagnetic in nature, which possess the unpaired electrons. This can be very smoothly explained on the basis of different ligand coordination that is taking place with the same central metal ion, that is cobalt 2+. When we talk about ammonia, it's a strong field ligand and hence leads to larger value of splitting of the crystal field, which creates a low spin complex, whereas when we talk about F negative, which is a very weak field ligand, in this case the rise in the low value of splitting and thus occurs the formation of high spin paramagnetic complex. In case of transition metal complexes, the d orbitals are outsidely seated and hence they can rapidly take part in the complex formation. Therefore, we can say the quenching of the orbital angular momentum easily takes place and hence only spin formula works well in them. In the case of metal of second and third transition series, this μs formula is not applicable, since there we also have a large contribution from the angular orbital momentum along with the spin motion, and thus μs formula basically is not used. Since the complex cobalt having ammonia as the 6 coordinated ligand is dimagnetic in nature, thus the magnetic moment is 0. But for the complex where we are having fluoride ion complexed as 6 ligands to the cobalt ion can be calculated as follows. N represents the number of unpaired electron. For the complex COF6 3 negative, N is equal to 4 since it is having 4 unpaired electrons, and the value of mu s comes out to be 4.90 bm, where bm stands for the Bohr magneton, which is the unit for the calculation of the magnetic moment. Now we will be discussing some of the limitations of the crystal field theory. Crystal field theory basically describes the bonding between the ligands and the central metal ion orbitals purely on the electrostatic basis. However, interactions between them is generally stronger than as expected. This is because in reality there is some sharing of electrons taking place between the orbitals or transfer of electrons from metal to ligand or ligand to metal, and so the interactions should be treated in terms of the bonding parameters instead. Hence, we can say that the most severe limitation of crystal field theory is its inability to account for the chemical bonding, since complexes may also be formed between neutral metal atoms and neutral or cationic ligands. Thus, due to the various shortcomings of the crystal field theory, it is not used nowadays. Some of the limitations can be summarized as follows. First one, it only considers ligand as point charge or dipole only. The second limitation is it does not take into account the overlap of the ligand and the metal orbitals. Because of these, the consequence is that it fails to explain that why CO, that is carbonyl, is a stronger ligand as compared to the cyanide ion in the complexes having metal ion in the low oxidation state. Basically, crystal field theory is not sufficient in explaining the electronic spectra of the complexes. Hence, we require a better theory, that is ligand field theory, which comprises of crystal field theory with that of the molecular orbital theory, which understands that the ligand and the metal overlap can be greatly accomplished when we consider in the form of bonding as well as antibonding orbitals taking place. Summary. In this module, we have basically studied the following points. According to the Jahn-Teller theorem, if the ground state electronic configuration of a non-linear complex is orbitally degenerate, the complex will distort so as to remove the degeneracy and achieve lower energy. The Jahn-Teller effect only predicts that which of the structures is going to undergo distortion, but it cannot predict what amount of distortion or the capacity, the geometry of the distorted complex will take place. Since Eg orbitals are having greater interaction with the ligands, hence Jahn-Teller effect is more pronounced in the case of Eg orbitals as compared to the T2G orbitals, which are there in between the axes. Jahn-Teller distortion occurs wherein the Eg level splits into a dz square orbital and dx square y square orbital, and thus the degeneracy of the Eg level is lost. There occurs a net reduction in energy or an increase in the value of CFSE, where the degeneracy is lost by distortion. The tetragonal distortion may occur either by elongation or compression of the x and y axis, or by the compression of a z axis or elongation of the x and y axis. The Jahn-Teller effect cannot say that which of these distortions which actually take place in a compound, since it varies from compound to the compound. T2G orbitals are also affected in distortion, but since they lie in between the axes, the extent of distortion is quite less. Square planar complexes can be imagined to result when two of the ligands present along the z-axis have been lost or removed from the complex, and this gives rise to only X and Y ligands present in the plane of the metal ion, and hence the coordination number changes from 6 to 4. The color in the coordination complexes is a consequence of the splitting of the d orbitals. Color of the complex basically depends upon the central metal atom along with the oxidation and nature of the ligands present. The magnetic moment given by the value of mu, which is given in terms of Bohr magneton, can be measured from spin-only formula in the case of transition metal complexes, that too of the 3D metal ions. The magnetic moment basically arises entirely from the presence of the unpaired electronic spin present in the complex. The formula mu s is equal to n plus 2 whole raised to the power half is quite well fed in this case, where n is the number of unpaired electrons present in the transition metal complex.